Hello and welcome to Unit 3 Mass Transfer Operations. In this video lecture, we'll be dealing with the learning with the extraction. So these video lectures are divided into on extraction are divided into three parts. This one will be dealing with the part 1. The next upcoming videos will be dealing with the part 2 and 3. And in part 1, we'll be learning about the basics of extraction. That is principle, material balance equations, equilibrium diagram, ternary equilibrium diagram, and the criteria that we require to select a solvent for extraction. Now, moving on to the principle, one by one we'll look into this. Now, when you say liquid-liquid extraction, as the name suggests, so you have two liquids here, liquid 1, liquid 2. We usually say two solvents. In one of the solvent, that is a feed solvent, feed solution, in that a particular material that we call it a solute is dissolved. The aim is to remove that solute from that feed solvent. For this purpose, we use another solvent, we call it as extracting solvent, and we add it, we mix it in a mixing unit, we mix it, then allow it to separate. For separation, you can use any force, gravitational force or centrifugal force. You can just leave it like that. They separate out. The two different solvents we have, the solvent, extracting solvent, and the feed solvent, they separate out. The reason is that the extracting solvent is immiscible with the feed solvent. That is how we have selected the solvent. They are immiscible with each other, just like oil and water. You mix oil and water, if you mix it, they get mixed, but after some time when you allow them to settle down, the oil layer gets separated from the water layer. Similarly here the extracting solvent separated from the feed solvent. Meanwhile, what happens, the solute what we have it in the feed solvent here get into this particular phase, that is solvent phase. This is the product, we call it as extract. It's termed as extract. The feed solution which remains with the low quantity of that original solute, we call it as raffinate. Now we can write the block diagram something like this. You have the solution, feed solution, you add the solvent to that, then when you mix it and separate, you get the extract and the raffinate. So extract is originated from the solvent phase, raffinate is originated from the feed solvent. So three things you'll be doing it here. First you mix them, contact, then separate, and then remove it and recover. For removing and recovering, you can use any other method, maybe a drying or filtration or membrane filtration, or you can use distillation to recover it. Most important part that you have to look here is solvent miscibility. That is, extracting solvent should be immiscible with the feed solvent. They should not mix with each other. So this is one of the complementary method, alternative method for distillation. So if you have difficulty in separating something solute out of the feed solvent using distillation method, maybe a heat labile or heat sensitive material you have, in such cases you can go for extraction. Now let's look into the material balance equation for the liquid-liquid equilibrium. So you have the liquid-liquid equilibrium process, you have the feed coming in, you have the solvent being added. As a result of that, you have the raffinate originating from the feed solution, you have the extract stream originating from the solvent stream. X is the concentration of solute in the feed and raffinate. Y is the concentration of solute in solvent and extract phase. Usually we take solute free basis. That means the quantity of the feed or solvent or raffinate or extract, we do not consider the solute in them, we consider without them. So that is called a solute free basis. If you consider that, F will be equal to R, because since it is immiscible, these two are immiscible, F comes out as it is without getting into the extract phase. Similarly, solvent doesn't enter the raffinate phase, instead it enters the extract phase only. Only the solute gets distributed between the raffinate phase and extract phase. So that concentration you can write it as XF and XR, YS and YE, where F and R are equal, S and E are equal. The reason for this is purely immiscibility. If they are completely immiscible, this is true. Alright. Usually this YS, if the solvent is pure, this YS is 0. So this is the initial condition. You have allowed it to equilibrate. The equilibrium condition is extract and raffinate. Then they are available at the equilibrium condition. The concentration of the solute in the two phases are XR raffinate phase and YE in the extract phase. Now if you write a balance, that's total balance, F plus S inputs is equal to R plus E output, and we know that F is equal to R and S is equal to E only under the case that they are totally immiscible with each other. This may not yield much of information, useful information for us, but if you do the solute balance, that is the solute entering is equal to solute exiting, so you can make a steady state material balance. If you do that, you get this equation, F into XF plus S into YS is equal to R into XR plus E into YE. In addition to this, we have one more information called as distribution coefficient. This is the relationship between the equilibrium, the two equilibrium value. The way you have equilibrium curve for adsorption, we call it as Freundlich adsorption or adsorption isotherms over there. Instead of that, we have almost a straight line in the case of extraction. So YE is function of XR, a linear function of XR, and that coefficient, the slope of that curve is K, and K is called as distribution coefficient. So K is the ratio of equilibrium concentration of solute in the extract phase. This is extract phase, Y is the extract phase, to the raffinate phase. Now let's solve a simple problem. You may pause the video here. You can come back after some seconds reading the problem. Alright, in this problem you have a picric acid solution. The concentration is given and you need to extract it using the benzene, and the concentration of the raffinate, how much you have to bring it down from 2, that is given 0.2 moles per liter to 0.02 moles per liter, that is feed and raffinate concentration. Distribution coefficient K is given 0.75. You need to find out quantity of benzene required for 1 liter of the feed. So feed quantity is given, it's in 1 liter. So XF is equal to 0.2 mole per liter. So the block diagram also you can write, same block diagram runs through all the extraction problems. Same assumption will make, that is two solvents are immiscible with each other. So we'll take it as a fresh extracting solvent benzene. So YS is equal to 0, quantity of S, that is benzene, how much it is there, we don't know, we have to find that, and we'll take F is equal to R, S is equal to E. So when you write the component balance, as I told you earlier, total balance may not yield much information, so straight away we can go for component balance. So the component balance, input, two inputs add it, two outputs you add it, and let us do the substitution from the available information. Note that F I have taken it as 1 liter and the concentration of XF is 0.2 mole per liter. So when I multiply the two things, the quantity is moles. Here also moles, total it's a molar balance. Another information what we have is distribution coefficient K. So the value of K is known to us. In this case, XR is given to us. XR, that is from 2.2 to 0.02 mole per liter. So based on that information, you can find out YE. So YE is 0.015. So in this equation, S and YE both are unknown. Using this distribution coefficient equation, you can find out YE. So you substitute this YE over here. You can calculate S. That S is equal to, upon simplifying this equation, you simplify it. Upon simplifying this equation, you get S is equal to 12 liter. The question is on quantity and the percent recovery. So you can find out percent recovery also, how much you have fed, how much is left out in the raffinate. That means how much has been recovered by the extracting solvent. The difference is how much has been recovered by the extracting solvent divided by how much it was present originally. So that's called as percent recovery. So based on the two information, XF and XR, based on this information you can find out the percent recovery, and it comes to around 90%. Alright, we'll move on to the another topic, related one, that is liquid equilibrium diagrams. Let us see what's an important issue over here. So liquid equilibrium diagram roughly looks like this, but almost a straight line. That's what the slope of this is, the distribution coefficient K slope, that is delta Y by delta X. Y axis is Y, gram solute per gram of the extracting solvent, X gram solute per gram feed solvent. You have to observe one thing here, whenever you take an equilibrium diagram, always The phase that refers to the feed will go to the x-axis. The phase that refers to the product stream goes to the y-axis. Usually here feed solution we have, so it is in the feed solvent. The product is normally extract, and that has got the extracting solvent, it has gone to the y-axis. So what is an important issue here? Just look at this. If k is greater than 1, that's slope, I'm talking about the slope. If the slope is more than 1, what it means? Extract phase has higher concentration than raffinate. That means concentration of the extract for the solute is higher compared to the solvent phase. Similarly, if k is less than 1, slope is less than 1. So in that case, product phase, extract phase will have concentration lower than the raffinate. And if they are equal, that means extract will equally extract the solute into its extracting phase, that is extracting solvent. So the concentration in the two phase during the equilibrium will be equal, that is y is equal to x in this case. One more way of drawing the uh, ternary equilibrium is the ternary equilibrium diagram, or we generally call it as Gibbs triangle or the equilateral triangle diagram. Now equilibrium triangle diagram, it's a triangle, equilateral triangle in fact. One end of that is apex. One apex is given for the solute, another apex it is designated for the feed solvent, another apex it is designated for the extracting solvent. The sides are equally distributed, so here it is going from 0 to 1, but if you write it in a percentage scale, it will be written as 0, 10%, 20, 30, 40, 90, 100%. So it is equally distributed. Same way it is the other two sides, it is distributed from 0 to 100% on a percentage scale, or on a decimal scale it is 0.1, 0.2, like that it goes on. Similarly other side. The apex refers to the pure solvent or pure component. So this particular point where I am pointing it out, that's the pure feed solvent. There is no other component in that. Here it is a pure solvent, extracting solvent. It is a pure solute. If you take the line, this particular line, which belongs to carrier, that is a feed solvent and the solute, this particular solid line, if you take it, it's a binary solution. That means solution has got only two components, solute and a carrier, feed solvent. If you take this particular line, it belongs to solvent and feed solvent. If you take this solid line here, it is belonging to the solute and the extracting solvent. So anywhere you take, it is a combination of two. Now if you get inside the triangle anyway, for example this, it's a ternary system. That means three components exist over here. So if I take this particular point here, some quantity of solute is there, some quantity of feed solvent is there, some quantity of extracting solvent is there. For example this point, if you take this point, how do we read this particular case? What you have to do is, you to find out any concentration, as I told you, that particular apex will be marked as full 100%. That means 1 is this. When it is moving away, it reduces. So on the opposite side of the apex, it is 0%. So on the entire line, it is 10% of solute, 20% of solute. Like that, if you do it, 70% of solute, 80% of solute, 90%, like that. So accordingly, this particular point is somewhere about 20, maybe 23%, maybe, yeah, 23%. So it's around 23% solute. And similarly carrier mole, this one feed solvent, if you take it, this particular part, opposite side of that is completely 0, 10%, 20%. So if it is on this particular line, it is 80%. So this particular point is how much? 52%. So the feed solvent is 52% for this particular point. Similarly for this extracting solvent, it is 25%. So total, if you add it, it will become 1 or the 100%. That is the speciality of this equilateral triangle. You add anything, any composition, it becomes 100%. So that means if you know the two, the third one is automatically calculated. You don't have to calculate the third one, it is automatically 100 minus sum of the two. So this is the equilateral triangle. How does it help us in identifying equilibrium diagram? Let us look into that. Now the important part here is we can draw the composition and find out whether it is miscible or not. So that's the advantage of this particular diagram. Let's see that. Now this is type 1 ternary LLE diagram. This is called as ternary LLE or binodal curve in general it is called. Now this particular curve what you see here, dark curve what you see, it is a binodal curve. It's within the equilateral triangle diagram. What it does is it bifurcates the whole composition, all possible compositions it considers this particular curve inside that means anywhere you take inside this region it forms a heterogeneous face. Means if you take any point over here it is not stable, that is all three things for this particular combination as you have seen in the earlier slide. Like this, for example, if this particular point for this combination 23%, 25%, 52%, if you take that particular combination it ends up with two phase. That means one solvent phase separates from the feed solvent phase, extracting solvent phase, that is extracting and raffinate, they separate out. Whereas outside the binodal curve within the triangle it forms a homogeneous phase. Let me assume that we have a point here. What happens if you take that particular combination, let me say it is 50 40 10 of three combination, 50 40 10 total is 100. So if I take that particular combination, what will happen? Simple, it forms homogeneous phase, means it does not end up with a two phase, it forms only one single phase. You cannot separate it out. What it means is you cannot select a combination outside this particular binodal curve. If you want to do the extraction, your combination should end up within the this heterogeneous phase. So you have two phases, two regions, heterogeneous region and homogeneous region. So you should be able to identify whether it is in the homogeneous region, homogeneous region here or heterogeneous within this one. Here the example this is taken is water as the feed solvent, acetone as the solute, and MIK, that is extracting solvent is taken MIK. Now this binodal curve has certain points here. One is plate point. This is the uppermost point of this uh, particular point. It's called, there is something called a tie line. We'll come to that particular thing a little later. So this tie line it goes on and this is the one point where it is about to become homogeneous. This is the end point you can say. This is the point where it is like it is tending towards homogeneity and heterogeneity. This is the end point of it. So that's called as plate point, extreme point. Another is tie line. Tie line in the sense you can convert a given heterogeneous feed into two homogeneous phases like this. For example, you have point at Z, you have a combination at Z starting with, if you have combination starting with Z, it is heterogeneous, it will form two phases. So based on this tie line it ends up with two phases, one here and another here. Now this particular line, this entire line is C rich phase, means extract phase. This is the extract phase. So this particular combination, obviously there are three components in this, that is B, C, A, B, C. All three things are there in that, but C is very high. It's very near to C. This point is very near to C, so it is C rich phase. That is C is the extract here. C is the extracting solvent, so it is extract phase. Similarly, this particular point A, B, C all are present, but B is in large quantity, so it's a B rich phase or whatever you write here, rich phase. Now water is our raffinate, that forming raffinate, so it is a raffinate phase. So you get to know what is the composition of extract phase, what is the composition of raffinate phase, starting with this feed composition. Then there exists something called as two-phase separation. These two-phase separations, when they are formed, we have something called as inverse lever rule that can be applied. What it means is, starting with Z, you end up with the X, that is raffinate, you end up with the Y, that is extract. Can we find out the quantity or the ratio of two quantities between extract and the raffinate? So that can be found here. You can see this inverse lever rule, xz distance, I mean the distance between this divided by zy. You can take a ruler and find out how much centimeter it is. Zy, how much centimeter it is. This zy distance, you can measure it. Take a ratio of that. It gives you a ratio, a number. That will be equal to amount of y divided by amount of x. Amount of y is nothing but extract phase concentration. Amount of x is nothing but raffinate quantity, uh, extract phase quantity, and amount of X means how much raffinate you have got, quantity, not concentration, it's quantity, moles or kg, like that. So it is opposite. You can see this xz gives you the quantity. Xz is in the numerator here, all right. Extract, the opposite side of it, extract is in the y, this one is in the numerator, right? So that's the opposite side of it. Similarly, yz is in the denominator, the opposite side of that is raffinate is in the denominator. So that is how the name suggests, inverse lever rule. So this is useful for identifying how much quantity you can end up with extract and raffinate. Now there is something called as type 2. Now if you see this one, type 1, you have two solvent, water and MIK, that is extracting solvent and the feed solvent. They are immiscible in this region, heterogeneous. You take anywhere in this region, add the two components, it becomes heterogeneous. Only small region here, small region over here, it becomes homogeneous. Otherwise for the rest of the concentration it is heterogeneous. So we have one pair of heterogeneous. Similarly this pair, the entire thing is homogeneous. It doesn't cut. This falls in the homogeneous phase. A to B, this line falls in the homogeneous phase. So you have two homogeneous pair and one heterogeneous pair, that is type 1. Whereas in type 2 you have two heterogeneous pairs, that is AB forms heterogeneous phase somewhere in between and BC forms heterogeneous somewhere in between. AC is completely homogeneous. So you have two pairs of homogeneous combinations. Here also you have two pairs. So this kind of system forms type 2 ternary LLE. Now a simple problem, you can pause the video and just read the problem and come back. This diagram is given to you. Alright, the question is this. Three questions are there. This diagram is directly given to you. This binodal curve is specific to a particular ternary system. So this particular system, this is applicable. Feed composition is given somewhere here. Feed composition is given, and it is said that it separates into two phases. Now the tie line here is parallel to the base of the triangle, that is BW. BW, okay, it is, so tie line is parallel. So you can draw a line parallel, you can call it as a tie line for this problem. Now the feed is given 40%, 20%, 40%. So you have to identify the feed, draw the tie line. The tie line is parallel to this line, and you have to find out the composition of organic and aqueous phase. So W is water, that forms the aqueous phase. B is the organic, right? Am I right? Yeah, benzene. B is the benzene, that is organic phase. Composition that you end up here, you have to find out. Another question is identify whether this combination separates into two phases. A combination is given, whether it is in a homogeneous region or heterogeneous region, you have to find out. And also you have to find out the plate point and its composition. Where exactly is the plate point for this curve and its composition, that you have to find out. Now this translate this entire thing into this way. So you have the feed and it separates into two layers, and two layer, for that you require a tie line. This is the tie line. The tie line is parallel to the base, right? And they have given Q and it falls somewhere here. This particular number, it falls somewhere here, and the plate point P. You just have to, what you have to do is you have to draw a line parallel, just move it upward, and the extreme point that you reach is the plate point. So this particular line, if you keep moving this extreme upward, so this will be the point, extreme point, and that's the plate point. The next part is you have to find out their concentration, E and R. R and E composition, you have to find out this R and E here, you have to find out. So R, if you look at it, A, this value is 0, 10, like that, it's going upward. So R 20%, right? 20% of A. And W, W is this somewhere here, 72%, right? This is 72% over here. W is moving this way, A is moving this way, acetic acid, and benzene is moving this way, 0 to 100. So you have to find out from the lines. Similarly, you have to find out for E, that is 5% water. E, water, W, opposite side. So here it is 5%, this line, and benzene, this line, it is somewhere about 75%, somewhere about 75%, and rest should be acetic acid. Next part, Q. This Q, if you draw this particular thing, that is 32% and 50%. Rest third one is not required. As I told you earlier, total is 100%. So it forms this particular point, and clearly it is out of the binodal curve. So obviously it should form a homogeneous face. Plate point, as I told you, you have to draw the point, then find out the composition of this, and accordingly EA that forms somewhere here, that is 48%. 48% of EA, and W, if you move this way, it is somewhere about like this. Sorry, P, W is this way, 0 to 100. You just find out W where it's 100, where from where the 100 is coming. That line you have to take it 0 to 100. So P, okay, somewhere here 20, 25%, yes. So rest must be benzene, 27%. Even if you don't look at it, just calculate this minus 100, you do it 100 minus 25 minus 48, if you do it 27% should be benzene. Otherwise, if you want to check it out, that is benzene moving from this direction, P value here like this, if you take it this line 27, somewhere about 27%, you get it. This is how we can use the binodal curve or ternary equilibrium curve. Now the last part, how do we select this extracting solvent? There are many criteria. Most important criteria I am listing it in the beginning. Distribution coefficient as large as possible. So what is distribution coefficient? K. It is the concentration in the extract phase to concentration in the raffinate phase. So extract phase concentration should be higher enough, always more than 1. Then another component comes called as selectivity, and it should be always greater than 1. Selectivity means you have two solutes A and B. Of that, A is your required product. Now what happens is, when you have a solvent, it extracts A as well as B. Both are extracted, but your requirement is only A. In that case, selectively your solvent should extract A and reduce the extraction of B. That ratio between these two concentration in the extract phase is selectivity. How much efficiently your solvent can separate A and B, or extract A against B, that you want to find out. So you just find out the distribution coefficient of A as well as B, take a ratio, that becomes your selectivity. Another is insolubility, immiscibility, what we call. So the highly, it should be highly insoluble. If you look at the ternary equilibrium diagram, there was a small region where they were homogeneous. There was a homogeneous region between extracting solvent and the feed solvent. Even that should be 0. That's most ideal. Recoverability, can you recover the solvent? Because solvents may be usually costly, so that is why we require more high relative volatility, or we expect that to be of volatile solvent, so that you can recover the solvent and you can get more pure product. Density, there should be a large difference, and you've seen the a principle that two layers separate out based on the density, based on the using gravitational force, they separate out. It's based on the density. If there's a large difference in density, it is easy to separate out the two quantities or two phases. Another is interfacial tension. Coalescence and emulsions, they form. Coalescence means they form bubbles and they break. If you have high interfacial tension, also problem. If you have low, also it is also issue. So it should be moderate enough. If you have high interfacial tension, what happens is it may not break. Breaking of the bubbles will be difficult. More the breakage, more is the surface area, more is the mass transfer. Chemical reactivity, it should be stable. The solvent should be stable, it should not react with any solute. And certain thermophysical properties should be low, so that you can operate it easily under room temperatures. Its availability and cost is also another important issue. Sometimes that may be overruled. Other criteria include toxicity, flammability. It should be low toxic or low flammable, you can say. It should be stable enough. It shouldn't be corrosive. It should be compatible with all your system that you're using. Now, another important thing in biotechnological processes that you need to know is, extracting solvent are usually not a single chemical. It could be a mixture of chemical. You may use a mixture of solvents. For example, if you want to extract certain lipids, we usually sometimes go for chloroform. Chloroform as the extracting solvent. That's one method. Or you can use a mixture of petroleum ether and chloroform, or some other combinations of ethanol and methanol. Different combinations you can use of different ratios, so that also serves the purpose. Yeah. It's the end of the this particular part 1. In this particular class, we have learned principle of extraction. We have seen how the equilibrium compositions are related in terms of xy diagram, as well as in terms of binodal curve, that is Ternary equilibrium diagram. We solved a simple problem based on the material balance equation and distribution coefficient. We have also seen how to identify, how to get the point within the ternary equilibrium diagram. Also, we've seen the different criteria for how do we select the extracting solvent. Thank you.